The Castle Rock Rainforest, visible in modern-day Castle Rock, Colorado, is approximately 64.1 million years old, taking place during the early Paleocene. In 1994, the discovery of the Paleo Rainforest was found by Colorado's Department of Transportation paleontologist Steve Wallace when he began surveying the hillside of Castle Rock in preparation for future road widening projects. He began to find large leaf fossils and contacted Kirk Johnson from the Denver Museum of Nature and Science, and soon enough intensive research and discovery was underway. Completed in November 2002, the Denver Museum of Nature and Science conducted a large-scale project by staff and volunteers as well as the Colorado Department of Transportation to excavate and collect the fossil specimens. After the fossils were sealed and transported to the Denver Museum of Nature and Science, they were cataloged and stored in the collection rooms of the museum so that they can be permanently kept on record. The rainforest resides in the D1 formation of the Denver Basin, which marks a significant time period in relation to the KT boundary. This discovery provides an insightful understanding to the rise of plants and ecosystems after the KT extinction from the abundance of fossils and marks surmounting evidence for a diverse base of plant species. This marks the first indication that an area in Colorado was once covered by a tropical rainforest, perhaps even the oldest one in the world. The discovery of the diverse base of plant species indicates a rapid evolution of tropical rainforests after the KT extinction and provides insight to the unique characteristics of the rainforest flora.
Castle Rock Rainforest is thought to be a significant finding not only because of the abundant, well-preserved fossil plant. It is also valuable to understand the complexity of the reconstruction of terrestrial food web from KT mass extinction. Compared to the low diversity of other Paleocene floras, the Castle Rock Rainforest proves the existence of unexpected high-diversity tropical rainforest in early Paleocene, 1.4 million years after the KT boundary. It is also the richest flora fossil site found from the late Cretaceous to Paleogene in the western interior. The margin analysis from Johnson and Ellis 2002 study gave an estimated mean annual temperature of 22.2 Celsius and the mean annual precipitation between 157 to 322 centimeters at the Castle Rock Rainforest, which is very similar to the well-studied modern tropical rainforest. It is closest to leaf litter samples taken from the modern rainforest at Manu in Peru, located on the west margin of the Amazon basin, and the Castle Rock Rainforest is actually occupied at a similar location relative to the Laramide Front Range during the Paleocene. Study about the spatial and temporal extent of the Paleocene dead zone reveals that there were no significant recovery of feeding in the first 0.8 million years of the Paleocene in the western interior. Study by Welf et al. 2006 indicated that nearly all the Paleocene samples have similar taxonomy, and the flora and insects damaged were typically in low diversity in many study sites. The 64.4 million years old flora from southeastern Montana shows extremely high insect damage richness. The insect feeding damage study on fossil leaves from Castle Rock also emphasized the uniqueness of this Paleocene tropical rainforest. Previous study from modern ecological observation shows a positive correlation between insect, herbivore, and fossil plant diversity, indicating the insect damage on fossil plants is useful to examine the Asian ecosystem and food web. The KT mass extinction causes a significant floral extinction, accompanied by a major ablation of insect-feeding morphotypes. However, they also found out the insect mining at Castle Rock is extremely low with respect to its plant richness, representing a low feeding diversity at this location. Another exception of more than one mine morphotype per species being found is Mexican hat, The Mexican head-mine morphotypes had host plant not related to its dominance, and 3 of them have never been observed in any other North American fossil floras. This suggests the Mexican head may include new and regional evolved taxa or long-distance migrants than regional KT survivors. Some other observations reveals fewer mines in Paleocene floras compared to the Cretaceous. Paleocene site from Wyoming contains all host plant founded at Mexican Head, but yielded only 7 mines out of 5,226 specimens. All the observations from the Castle Rock and Mexican Head floras show a remarkable and localized deviation from theoretical pattern of stage food web recovery, representing an unbalanced food web recovery occurred after KT massive extinction.
The Castle Rock fossil assemblage depicts a previous environment very similar to modern-day tropical rainforests. The fossil leaves from Castle Rock are generally very large, indicative of high mean annual precipitation in the region. Some of the leaves also had drip tips and thick cuticles to facilitate the drainage of dew and prevent rotting. Additionally, the ecosystem was dominated with plants that had smooth leaf margins, indicative of high mean annual temperatures. The fossil assemblage also suggested high species richness and spatial heterogeneity. The Castle Rock flora is also unique in its preservation. Kirk Johnson, Beth Ellis, and Reagan Dunn reported that the dominant morphotypes remained consistent vertically along the column, but varied widely laterally from quarry to quarry. This suggests that the rainforest was preserved in situ. If the leaf litter was transported away from the site of origin, there would be little variation in morphotypes across the region. The leaf litter was preserved in 3 distinct leaf mats over a layer of poorly developed paleosol containing tree roots and evidence of bioturbation. The first and second leaf mats contained rooted tree trunks preserved in a finely laminated siltstone. The third leaf mat was preserved in a laminated sand and siltstone with ripple marks and flazer bedding. This region also contained roots and evidence of bioturbation. The 3 leaf litter mats are interpreted to have been deposited by a series of 3 overbank floods over a relatively short period of time, anywhere from hours to weeks. The transition in class size from siltstone to sandstone indicates the third flood was more energetic relative to the first 2. The transition in class size from siltstone to sandstone indicates that the third flood was more energetic relative to the first 2. Above the last flood deposit are layers of bioturbated sand and mudstone with ripple marks indicative of a floodplain environment. The dominant morphotypes in these younger layers are already different than the ones in Castle Rock rainforest. Over 100 morphotypes have been discovered in Castle Rock. The dominant plant groups uncovered were dicots, cycads, conifers, and pteridophytes. Dicots constituted 94% of the assemblage, and many are new species distinct from today's species. However, some relatives of modern plant families have been found. Examples of these plant families include Platanaceae, which incorporates sycamore trees, Lauraceae, which incorporates tropical avocado trees, Iliocarpaceae, which include tropical and subtropical perennial trees and shrubs, Tiliaceae, which includes temperate lime bushes, Sterculiaceae, which includes the tropical cacao tree, and Urticaceae, which includes various flowering plants like stinging nettle. We hope this video clearly demonstrates the uniqueness and significance of the Castle Rock rainforest in Colorado. This unusual Paleocene landscape supported pseudotropical conditions that allowed a dense and diverse population of plants to flourish at high latitudes. The unique way in which the rainforest was preserved provides volumes of important ecological information. This information can help us understand population recoveries after mass extinctions and potentially provide us ways to ameliorate the current mass extinction. We enjoyed having the opportunity to observe remnants of this prehistoric landscape, and we hope you enjoyed this video. We would like to offer a special thanks to Dr. Peter Wilf, Dr. Ian Miller, and Dr. Herbert Meyer.